minus 2f delta f cosine theta. You'll notice all the terms in parentheses have 2's. I can factor the 2 out and divide by it. So over on the left-hand side, I'm going to have a 1/2 m squared v squared. And that's going to be equal to, well, I got h squared over c squared. All my 2's have gone away when I divided by it. I have over here f plus 2 delta f, the 2's gone. F plus delta f minus, well, if I factor cosine theta out, I'm left with, oh, that should be f squared plus f delta f. I factor cosine theta out and the negative sign out, I get f squared minus f delta f cosine theta. And I can factor it one more time. That should be a plus sign right there. I can now factor f squared plus f delta f from this and from this. And I'm left with 1/2 mass of the electron squared times the speed after the collision squared is equal to h squared over c squared times f squared plus f delta f, 1 minus cosine of theta. If I divide by the, well, actually, we'll come to that. No, let's go ahead and do it now. I'm going to divide by the mass of the electron by one of them. So I end up with a 1/2 mv squared, which should be a formula familiar to all of you, over h squared over mc squared times that. I'm going to leave it like that for now. So f squared plus f delta f, 1 minus cosine theta. And that's pretty much as simplified as we can get for just conservation of momentum. Questions, speaker? All right. Conservation of energy. Energy initial equals the total energy final. Energy initial equals energy final. There are no non-conservative forces involved. The particles don't actually touch each other. There's not like a normal force there. They repel each other. So initially I have just HF. That's because the electron's not moving, I'm not worrying about potential energy, is equal to HF plus delta F, which would be the energy of the photon after the collision, plus 1/2 mv squared. From this, 1/2 mv squared is equal to hf minus hf plus delta f, which equals negative h delta f. So from conservation of momentum, I have this equation for the 1/2 mv squared, and from the conservation of energy, I have this for conservation for 1/2 mv squared. I can now set them equal to each other, and h goes away. And so I'm going to set this equal to negative h delta f. Dramatic pause for questions and people to catch up in writing. Anyone need to hang on this page a little bit longer? So h squared c squared. So like h squared mc squared f plus delta f squared plus f delta f, 1 minus cosine theta, equals negative delta F. I'm now going to divide by this. It's now a matter of what form do we want the final thing in. So I'm going to divide by this, so I get h squared over mc squared times 1 minus cosine theta equals negative delta F over F times F plus delta F.
Would it just be H if you cancel?
Yes, it would be. That's right. There was an H here. So that goes away. Thank you. Okay, I got a fraction right here. My denominator factors. My numerator is part of one of those factors. How do you break a fraction up into a sum of fractions? And I'm blanking on the math term for it. Separation of, not separation of variables. Whatever it's called. Seeing the wheels turning. So we're about to come up with an answer somewhere in the back of your mind. You remember doing this? You would have done it at some point in Calc 2.
Could you just multiply both sides?
Yeah, that's not really going to help us any. Then we just end up back here again.
Oh.
I'm going to break it up into a fraction of something over F plus something over F plus delta F.
Would it be like negative change in F times F plus change in F parentheses?
So what's going here?
Negative change in F.
And here? Okay. All right, so here's the technique. That might be right. For right now, I'm just going to put A and B here. I don't know what A and B are. That's what we're trying to figure out. If I look at just this piece right here, I multiply everything by this full denominator here. And so I have negative delta F equals A times F plus delta F plus B times F. So if I multiply everything by this denominator here, F cancels out, so it's just A times the other part, and the F plus delta F cancels here, and I'm just B times F. So this is equal to AF plus A delta F plus BF, which is A plus B times F plus A times delta F. If this is equal to this, then A equals negative 1. A plus B equals 0. So we have A is equal to negative 1, A plus B equals 0, so therefore B equals 1. So I've got my H over MC squared, 1 minus cosine theta is equal to negative 1 over F plus 1 over F plus delta F. Taking that next step. If I multiply both sides by c, the speed of light, I get hm over c, or h over mc, 1 minus cosine theta, is equal to c over f plus delta f minus c over f. I switched the order in which I wrote it because the whatever f was a negative. What is speed of light divided by the frequency of the light?
Length.
What'd you say?
The length.
Yeah, wavelength. Yeah. So this would be, well, f was my initial frequency, so this is my initial wavelength. This is c divided by my final wavelength, so that, divided by my final frequency, so that's wavelength final. So this is just change in the wavelength. So the change in the wavelength is equal to h over mc, 1 minus cosine theta. And so now you can set this up, you get some sort of atom with a bunch of electrons, you shoot light at it, and then you put a detector and you measure the frequency of light that comes off at particular angles. This is the formula associated with Compton scattering. And again, the premise of it that matches experiment is that light is behaving like a particle. So we now have more evidence that light behaves like a particle sometimes. If I jump back to the first page. We've done those. These three right here I'm definitely not going to go into. These are connected to each other, so we'll talk about that first and then the other one. Specific heat, if it's a monatomic, it's a molecule that's composed of a single element, single atom. Classical physics does quite well doing specific heat. However, once you start getting more complex molecules, classical physics falls apart. Bremsstrahlung is sort of a reverse photoelectric effect. It is, instead of light ejecting an electron, it's an electron creating light. So if I shot electrons at you and I had a barrier between, so that when the electron hit the barrier, the electron would stop, radiation is going to come off of it. I don't know if your parents ever told you to stay 6 feet away from the TV. You got it, you got it. TVs aren't designed that way anymore. But that comes from the fact that electrons were being shot at the TV screen, and then because they were being stopped by the screen, you have basically the electric field changes rapidly there, and so you get radiation coming off of that. That's the root of it. But TVs now, I know they evolved from shooting the electrons towards you, and then eventually got to the point where the radiation was shooting out the back, and now I'm not quite sure what the radiation situation is.
Now it's like all LED based, so.
Yeah, it's less dangerous than it used to be. All right, into here. So if I have a charged particle that's oscillating, what's going to happen? If I have a charged particle just moving back and forth like this, what's going to be the result of it? We've talked about it more than one occasion. Chapter 34.
Current?
Pardon? I didn't hear what you said.
A magnetic field.
Eventually. How do you get the electric field by a charged particle moving back? Sorry, how do you get the magnetic field by a charged particle moving back and forth?
Because a current would be a moving charge, right?
Ah, that's where you're going with that one. Okay. All right, I'll go with that. I was thinking of, I have an electric field, I have a charged particle moving back and forth, so I have an electric field constantly changing. The electric field changes, which means the electric flux changes. The electric flux changes, that means I create a magnetic field. If I'm oscillating back and forth, the magnetic field is gonna change. Probably gonna skip a couple steps there, going with what Sarah said. The magnetic field is changing, therefore the magnetic flux changes, which creates an EMF, which creates an electric field, and basically it's the production of an electromagnetic wave. As we discussed, electromagnetic waves have energy, depending upon the frequency. So if I have a nucleus here, and an electron zipping around like that, it should be giving off radiation. Well, if the electron's giving off radiation, what should the electron be doing?
Moving down energy level.
Yeah, well, at this point, they're not aware of energy levels, but yeah, it's giving up energy. The electromagnetic wave has energy, so that electron should be losing energy. And if the electron's losing energy, what should it be doing?
Going slower.
More specifically, what are the implications of going slower?
Cooling off.
If the moon were losing energy, what would it be doing?
Falling towards the center.
Yeah. So according to classical physics, radiation should be given off, which means it's losing energy, which means that electron should be spiraling in. But obviously, it doesn't do that. Otherwise, the electrons would have all disappeared into the nucleus long ago. In which case, photoelectric effect never would have been seen. So, let's do the history of the atom. One of the first sort of modern views of the atom was, the model was called the plum pudding model. J.J. Thomson, who discovered the electron, had this idea, excuse me, that he knew electrons existed, he knew about positive, negative charges, so he pictured that an atom was just this sort of a sea of positive charge here, just this mush, like pudding. And the electrons, which he, since he discovered it, he knew was a particle, you would have these electrons just sort of mixed inside of it. Like raisins in plum pudding, thus the plum pudding model. Now, if I have this atom, the gelatinous mess with these electrons like raisins sitting in it, and I fire something heavy at it, what would you expect the heavy thing to do? Pardon? Push it?
Or piercing.
Yeah, I'm thinking more piercing. So thinking about like let's make it morbid, a bullet going through you. So you would expect that if I took a heavy particle and shot it through there, it would just go plowing right through. It might deflect a little bit because it might hit an electron, but if it's more massive than the electron, then, well, the electron goes zipping off, but this thing should go right through it. So Rutherford created this experiment in which he took gold foil, which, think of aluminum foil, it's made of gold. Took gold foil and shot alpha particles at it. Alpha particles, we now know, is the helium nucleus. Got 2 protons, 2 neutrons, considerably heavier than electrons. And they shot alpha particles, and then what they did is they had a detector, he got grad students to do this, had a detector over here to basically see the alpha particles that are coming through. And then you move it over here and you see the alpha particles, and you basically work your way all the way around and you see how many alpha particles come through. One of the grad students who was doing this was Geiger, of Geiger counter fame. So you can imagine his inspiration for trying to come up with an easier way to detect radiation. Rutherford had 9 grad students who eventually went on to win Nobel Prizes. Geiger was not one of them, even though he was one of the most famous of them. All right, So what he noticed is that most of them went through without a problem, but occasionally one would bounce backwards. The analogy that's often used is if, imagine shooting a cannonball at a tissue paper, and occasionally the ball would bounce back. Now, personally, I suspect Rutherford suspected this was going to happen sometimes, because why on earth would you detect behind it if you didn't expect it to happen? But Rutherford's probably the greatest physicist who never got a Nobel Prize in physics. Got one in chemistry, though. He referred to all sciences neither as physics nor stamp collecting. So I don't think he was particularly fond of chemistry. But he got the Nobel Prize in it anyway.
I do remember some of this from chemistry textbooks,
Okay.
so.
Well, this was considered the big experiment to tell us that there's a nucleus. One of his proteges, another Nobel Prize winner, Niels Bohr, Danish physicist, I believe, took on the speculation that, and again, it ultimately it bore out, it came up with an answer to not only the discrete spectra, but why electrons don't go spirally into the nucleus. But I never read any of the history about why he decided to try this. But he came upon this idea that the angular momentum of the electron going around the nucleus is proportional to Planck's constant. And I'll make sure I'm not leaving something off there. Not H, but H bar. Now, H bar is indeed different, but H bar is Planck's constant divided by 2 pi. It shows up enough. And n is some integer. So let's explore this a little bit in the little bit of time we have remaining. So I have some integer times